Hi there, welcome back to the channel. Welcome to the second video in the restoration series for this Grundig 2140. I've gone further ahead than I thought I would in an area that I didn't think I would go. In other words, I've actually focused a little bit on the cleaning at this stage, which is rather unusual. And the reason is I got a bit carried away with my airbrush compressor cleaning method, which I'll show in this video if you're interested. And I found that it was actually a good idea to get the chassis cleaned up so that I didn't have to look at all the grime as I go through the components and all the actual restoration. So that's one of the aspects that is covered in this video. The other one is I went back then to the basics of checking the audio section, or rather the power amp section, and I found a few surprises. I'll also just give you a hint. My DIY tube tester came in handy on this one. Unfortunately, because I found a tube that's going to have to be replaced, and tubes are getting quite expensive these days, as you probably are aware. I won't give too much away. If you're interested, stick around and see the video. Just a warning, there's a bit of schematic description. You can always just fast forward on that if you're not interested. So stick around, enjoy. But before we carry on, I just want to thank the sponsors of this video, PCBWay. If you come to the website and you want to see some of the projects that I've done and use the PCBs that I've actually produced, you go into the shared section, and here you can search for the PCBs or the PCB projects that I've done. Not only mine, but probably thousands of other projects that other users have created and have made the PCBs available for you if you'd like. One of the things that really attracted me to them is that your PCBs can be extremely well priced and with very fast turnaround time, and you can do a simulation exactly what you want on your order, so there's no doubt when you're working on a project how much you're going to spend on it. The other area that's looking interesting to me is the CNC section, where you can do CNC milling by sending up a file in any of these formats, and again you do the same thing. You tell them what material you want. So here's another example. You can get your 3D printing done with them. But overall, their products and capabilities are endless and their prices are extremely good. So whatever you need, go over to the website and I'm sure you'll find something for your needs. Let's get back to the video. Let me quickly explain what I'm doing here. I obviously want to start with my normal procedure, which, as I've mentioned endless times before, is power supply, then the audio, then the radio. But I started working on these, or starting to remove these components on top here. And I decided to give this a bit of a cleanup first because it is incredibly grubby. And I got this ready to do my usual, but I want to show you what it is I'm doing and how I'm doing it. I'm using that air compressor, as I mentioned before, to clean this. But so let me show you just quickly. I removed this faceplate. This is going to need a coat of paint. That goes with just 4 screws on here. The magic eye is on the back. It's obviously the other way around, something like this. There's a little bit of fishing line here that's still stuck because it holds the needle in place, the indicator. But I want to show you how I get on with the dirt. Let me just give you a quick description. I've got these brushes out. Now, 2 of these 2 end ones are natural hair brushes from an artist shop. They are natural bristle. This one's actually a nylon or plastic or something like that, but it's a lot rougher, and I found that sometimes it's useful to be able to sort of scrub when the dirt's a bit too ingrained. I've got a little cup here for some alcohol. This is just the normal alcohol. At this stage I use the cheap stuff. I've got my air compressor sitting over here and it's all ready to go. I've got some of that same alcohol in here, and let's see how we get along. So firstly, I'll start brushing off with this alcohol using this brush. Now don't worry about cleaning away the residue. I'm just giving it a good scrubbing. I've got a little cloth here that I'll sort of clean the brush off every now and then with. And it's coming off. This This chassis is sort of a dark finish. It seems to have had a coat that that has worn off. As one of you mentioned, by the time they were building radios in 1962, I do believe they were cutting a few corners on the quality of the finishes. You can see that. You see, I've given that a good scrubbing, and now I take my airbrush with alcohol in it. Needs a bit more. It's finished. Give it some more alcohol. And really just rinse it all down. If necessary, I can scrub a bit where I think there might be more dirt. I think there is a bit more there. And obviously this dirt is running to the back, so I'm going to have to wash from the front to the back. Sometimes I actually put this on its side at the end, give it a final brushing. But look at this. There you go. Brilliant. This is one of the tools that I'm happiest with recently because it really works like I expected it to. It makes, the cleaning still needs a brush. You still need to brush it, but the difference is that you don't need to dry it out or clean out the residue with cotton buds or cotton swabs or one of my chopstick tools with a cotton thingy at the end. I can still use that. Obviously all these tools are not mutually exclusive. They just add to the arsenal. There we go. And this thing is not strong. It's not a strong blast, so it doesn't damage any wiring or anything like that. And it does let me get to the thin wires as well. Okay, I'm going to do a bit more cleaning because I do want to start at the top, and then as I go down, I want to get these components out of here. I want to have the top cleaned out so I don't have to look at all this dirt when I get into the actual restoration. Now, why am I doing this cleaning before I actually restore it? Well, I know this thing is going to work. Okay, it's a little bit big-headed of me to say, but I do know that I'm going to get this thing to work. We've seen that a lot of it is working already. I'm not too afraid that that I'm going to go down a rabbit hole and not get this thing to the end, which is when I would normally clean it. But anyway, as I go along, I clean bits and pieces, and when I get to the end, I've got nothing left to clean, which is always a relief. Let me get on with it. Right, we're back. And I will not blame you if you accuse me of having got carried away. I did get carried away with some of the cleaning. Let me show you what I've done. This front panel was, as I mentioned, removed. 1 screw, 2 screws, 3, 4. That was removed. I cleaned it out and then resprayed it with this off-white paint. It's sort of creamy paint. It's lighter than what was there before, but I'm sure it sort of gets yellowish with age. So I'm happy with that. It came out beautifully. Put all that back. I put in all the these pads thingies that were all dried out, cleaned them out, replaced them with this cloth tape. That's just to create some sort of padding when this thing goes into the cabinet. Actually, this is where the cat's having fun. This is where the faceplate touches. You don't want it to connect directly to the metal. The piano keys, once you've done that, you think, well, why should I not do this? And I decided to clean out the piano keys, which cleaned out beautifully. The tone control and volume control, those got degreased. They were pretty tight. So I put in some WD-40 to loosen it up. And then at the end, just a little bit of machine oil, just a drop there and a drop there. So now they are nice and smooth. The tuning is just a spindle over here, and it's smooth. There's nothing holding it back. I still have to see what's wrong inside because this thing is jammed, and I'll worry about that later. I don't want to get too carried away from what I'm trying to do, which is trying to do the power supply. And this top section, it's all been cleaned. It's all been cleaned. I got carried away with my little airbrush compressor. It really is great. I love it. And it just makes life so much easier. So that got all cleaned out. All the wires got cleaned out. There's a little bit there. I might have to go back on that. And then I replaced these components here. There were two capacitors here. There's a big resistor here, which is perfectly fine. And there's a small resistor here, which is also perfectly fine. I'll show you that in a minute in the schematic where that goes. But at least that part is done. So when we look at this radio, it looks like something completely different. Let me show you from the back. There we go. It's cleaned. This color, this sort of dark color, this metal, it doesn't come out. This is not rust. This is the coating. There was some sort of coating, plating on here. You can see it on there. I think it's, I'm not sure what it is actually. I've known, but I've forgotten. That's obviously worn off, and this is the result. A little bit unfortunate, but that's what it is. It's been cleaned out. All these were cleaned out. Obviously at the end you've got to give it another little touch up on all this, but at least it looks a lot better and I can get on with the actual work. Just one more thing I want to show you. This part is always a little sensitive, a lot of small wires here, so you've got to be careful. And again, with that airbrush compressor and the brush that I use, you can do that perfectly well. And that's what's happened. It's now looking great. So what did I do as far as restoration is concerned? That's it. That's what I've done. You can't see anything, right? Well, that's the idea, right? I replaced, or I restuffed, that filter capacitor which is on the inside. What you see here is the exact same B+ coming out of the selenium rectifier, going into the first filter cap, and the second filter cap's also taken off here. Now, I'll show you the inside in a second, but this selenium rectifier I normally leave to the end. It's working, so I know it's working. I would like to replace it, but when you replace this with 4 silicon diodes, a bridge rectifier, you have to put a resistor in series to drop some of the voltage that the selenium rectifier was doing in this position. But you don't know how much voltage to drop because, or rather, you don't know what resistor value to put in because you don't know how much current this is drawing. You could do it now, but when you restore it, it might actually change the balance of the circuitry and your current draw might be different. So I'll leave it to the end. At the end, I'll see what voltage I've got, replace this, and then adjust as needed. So let me show you the underside of this thing. Now that has been replaced or restuffed. This filter can, I removed it by desoldering it on those wires on that end and bending out those lugs that sort of you bend it into the chassis. Removed the front. It takes quite a lot of work with a sharp, very thin screwdriver. You can open the top, pull the innards out, clean the inside, then replace it with 2 47 microfarad at 450 volt capacitors and put everything back. I've done this a lot. I won't go into too much detail. I don't think it's necessary. You've seen me do that. But as you can see, it turns out to look exactly the way it was. Even the closing in there, because this is on the inside, you can almost not tell that it's been moved at all. So that is done. And now I have a ripple-free supply, hopefully. I wasn't hearing much hum. Mind you, we didn't listen too much for it anyway. But at least those filter caps have been replaced. And I know the switching is working. I've actually followed the mains from the mains lead through the switches. I've cleaned these switches with deoxit and reacted, just worked them endless times here to make sure that they're nice and clean. The supply then gets to the transformer and then it goes through, the fuse is fine, it goes through, comes out the secondary, and then goes to the selenium rectifier. And then of course the filter capacitors. So that part has all been done. And I just want to now switch it on and see if I've got a reasonable B+. Let's have a look. The schematic calls for about 250 volts, 245 I think it is. On medium wave, it's slightly different on FM because the FM tube draws a bit more current. But let's see what we get with no tubes in. Okay, let's switch it on. Right, I'm all set. I've got medium wave or long wave selected over here. So we've got the switch, the power switch is on. I've left the magic eye in there because it helps to discharge the caps at the end, just to make it a bit safer. But I've got this, the multimeter measuring B1+. It's right at the output of the selenium rectifier, which also means the first filter cap. And with the tubes and everything operational, we expect 245, I think it is, volts. Let's see what we get. I'm going to give you this wide angle shot so you can see the dim bulb tester. And I've got one bulb on here, so I've only got the 40 watt bulb on here. It's very restricted. The supply 230 as we expect. And I'm going to hit it. Okay, there we go. 280 volts. Obviously that's high because there's no draw. There's no current draw really, except the magic eye which has come on there. That magic eye is actually in good shape. So 285 volts. This thing's working. It's working fine. And if I measure at the second capacitor, I should get pretty much the same because there's very little current draw. So there's capacitor 1, 288, capacitor 2, 286. Perfect. So far so good. Now what have I done? Let's look at the schematic and see where we are. Here we have it, the schematic. And as you can see, I could not resist. I've done some painting. Let me show you what I've done here, and I'll show you what we're actually going to be looking at more closely. So obviously here we have the output. Here's the speaker. I have checked all these connections. That's why they're painted green. There's actually one more here that is connected, the ground, to that speaker connection. I know that's the case because when I put the speaker at the back, I could hear the sound. And that follows through to here to, on a feedback loop or path, which we'll be going into a bit more detail later. The primary sees us taking the B plus from here, comes out of here, goes to the first filter cap over here, and then it goes up into the output transformer, through the primary of the output transformer to the anode or the plate of the EL84 power tube. It then, from when it comes into the transformer, it goes through another small winding of the primary, on the primary of the output transformer, which is basically an inductor to help smooth and remove ripple, AC ripple. It goes through a 1.3K resistor. It's that big orange one at the top, or red one at the top, which is in perfect condition. And that in turn goes to the screen grid. And that's all there. I've checked it. I've also checked this line and I've replaced these two caps. So what I can do is actually just finish this because I haven't kept up to date with this thing, have I? And the way I do that is in Adobe Acrobat Reader. I've got comment over here. So I select comment. I'll just push that to the side so I don't have that in the way. Now that I've got this set to comment, to allow comment, I can use any of these guys at the top here. And so I'm going to use the polygon, and I've checked this line over here to the second capacitor. I've also checked this to the first capacitor. I've checked the capacitor to ground line. And I've replaced the capacitor, so for that I use the line and I make a red line to indicate that I've actually replaced it. There we go. Okay, so I know that I've done that. I know I've replaced this guy. What about this? This is that capacitor at the top there, on top of the, this was the smaller one on top of the transformer. What this does, this is 4.7 nanofarad, and what this does, you can imagine that this tube is producing the full range of frequencies that it is capable of producing. Some of them are at frequencies that our speaker won't be able to pick up, that we won't be able to pick up. So what this does is it actually shorts out some of the high frequencies going into that transformer. It doesn't allow those frequencies to get transformed, passed on to the secondary. It just cuts off certain frequencies above a certain range. The 4.7 nanofarads is the value they've chosen. If you made it a smaller value, you'd get more high frequency content going through. If you made it a higher value, the sound would be bassier. It also obviously has the effect of avoiding oscillations that can happen at this point, okay? This resistor here takes your B1 plus and drops it through a resistor to that capacitor. It's basically a pi filter, right? Resistor, capacitor. And it filters a bit further, but it also drops the voltage a bit because all the current that's going through this resistor is going to supply the entire circuit. This is our B2 plus all the way here. So the more current that flows through here, the greater the voltage drop. So the greater the difference between our B1 plus and our B2 plus, between those two voltages, okay? At the moment, when we looked at it, there was very little difference between those two voltages because there's very little current flowing through here. No tubes were in. Now, what about this thing over here? Well, the way this works is this is a feedback circuit from the output. From the speaker, it goes through here through a 3K3 resistor. This is also at the top of the transformer. That was also reading perfectly fine. And there was also a capacitor over here, which is switched to ground. This is 150 nanofarads, which is actually quite high. And what this is, and it was replaced. This was the one that was basically bubbling at the top there. What this is that when you select anything other than FM, this switch is made. It's closed like this. So when you've got long wave, medium wave, short wave, some of the high frequencies from your speaker, instead of going through your speaker, are bled off to ground. It sort of dampens the frequency range of your speaker because those bands, short wave, medium wave, and long wave, don't have high frequencies. It's AM and it's pretty poor quality, but you're just taking it off the speaker so that you get a duller sound. You don't get so much hiss. Okay. When you select FM, you expect better quality. You expect a bigger range of frequencies to come out of your speaker because your FM is more high fidelity. Okay, a bigger sound stage, as it were. So that switch opens and that capacitor disappears. Okay, or disappears from the circuit. This section here still goes through, and we'll look at that when we look at the power amp stage and the preamp stage. But that is what I've done so far. And down here, we've actually got our power supply. Now, what have I done here? Well, I can paint stuff, right? I can paint stuff. I know that this is working, and I'm using that one fuse, and I know that fuse is fine because we are getting this thing's working all the way through, okay? I know that this thing's fine, but I'm going to leave it, and I know it's connected to ground, but I'm going to leave it here in the meantime. I'm not going to mark it because I don't know whether I need to change it, and I might need to change it at the end, depending on what the voltage, the final B plus is. I know that the heater, this is the heater supply. I know, for example, that the light bulb is working, okay? I definitely know that is working. So I can paint it, all right? I happen to know that these heaters are working as well, but I'll leave that for now. So we've basically checked our schematic all the way, or rather our circuit, from the input of the mains through the power transformer. We get two outputs, the high voltage output and the low voltage heater supply, which is low voltage, high current. And it goes to the first filter cap through into the output transformer, into the power tube, and then it also comes out here and goes through a resistor to the second filter cap, which has been replaced. It's the ones I've stuffed. And we know that all this is good, and we're getting a voltage. We're getting a voltage both here, which there it is. That there says 245. Now, what does that mean? There's something here. I saw it before. There's three readings on here, right? And if you look at the schematic, here we go. You see that? In a closed box is with medium wave set. In dashed lines, it's FM. And in that circular one, it's pickup, okay? And that's exactly what they mean here when they have this. That 245 volts, 62 milliamp, that is the voltage at the B1 plus when you have medium wave selected, and it's drawing 62 milliamps at this point. If you select FM, that's the dashed lines over here, it's 238 volts, 71 milliamps being drawn. And if you choose the pickup, you should read about, well, 244 volts, almost the same as the medium wave, and it's a 62 milliamp draw. That just gives you an indication so you can check later. That's why they have this legend with three voltages. Somebody asked me that recently. The other thing is the fuse, the SI, is for 220 volt supply, 300 milliamps. For 117 volts, which would be the States and other places, 600 milliamps. Now, I don't have 220 volts. I've got about 240 volts, 230 volts rather. So I'm still leaving the 300 milliamps, and I've checked that's what's on the fuse. But I'm expecting, or I should expect, that the voltages here will be slightly higher. In other words, instead of 6.3 volts AC for the heater supply, I might get 6.5, 6.6. But again, I will see that later when this thing is stabilized and it's under load. You can do something to it. You can put a resistance series here to drop the voltage slightly. I have found that you normally don't need to, but we shall see at the end, as I mentioned when I talked about replacing this guy. Okay, now what do we do next? Well, this is my routine. The next stage that I look at is the power amp, and this is the power amp. This is it. This is the power amp. You've already checked the link that the power amp, the power tube, has to the output transformer and out to the speaker. But effectively, this is your power amp. And what this does is it takes whatever signals on here, superimposed on a DC voltage, because it's coming out of the plate of the preamp tube. It takes whatever audio signal is on there, it passes it through a capacitor, so you get rid of the DC, and you only have the AC going up and down here. And then it goes into the grid of the EL84. It's got a grid stopping resistor, a 1K, that's just to ensure, it basically helps to reduce oscillations. And you've got a 1 meg grid bias. This tube needs a bias to ground. But effectively the voltage, the DC voltage there is 0 volts, effectively. Okay? Because there's very little current that flows in or out of the grid. DC current. There's very, very little current at all, in fact. The tube is a voltage controlled device. Like a transistor is a current controlled device. Small current in, big current goes through. That's a transistor. In this case, voltage goes in, current goes through. Okay? So you've got a voltage here that's going up and down, and that's your audio. But DC, it's on 0 volts DC. So how does this work? This thing needs bias. It needs a negative bias between the cathode and the grid. And the way it works is you've got a resistor here. This is a wire wound resistor, this symbol. Okay? And it's 0.5 watts. I mean, if you replace that, you probably use a 1 watt resistor. I normally put a 2 watt resistor in there because I've got them. And it's 140 ohms. And what this does is it creates a current that passes through here. Once it's fed with B plus up here, creates a voltage drop over there, so that your cathode voltage there would be whatever the voltage drop is across that resistor, reference to 0. That's ground, right, over there. So let's say you've got 5 volts, okay? If you've got 5 volts drop across there, it means that your cathode is at 5 volts. Your cathode's at 5 volts. Now, relative to your grid is at 0. So the voltage between the grid and the cathode is 0 minus 5. So it's minus 5. So the tube is in class A mode. It's basically pinched off. It's like a hose pipe where you put your foot on it and it's reduced the amount of water that's going through. There's some water going through, but you've reduced the amount. And now that voltage that's going up and down here with the audio is you moving your foot up and down, right? And more water flows through and gets pinched off again as you sort of thump with your foot, lift up and down with your foot in rhythm to the music. That's what this is doing. Okay, I've turned this to a hose pipe. Geez, Manuel, I'm getting crazy in my old age. So that's what's happening with this tube. Now we need to check that resistor. We need to check those resistors. We need to replace that guy because that's the real bugger. That one there, that's the one that kills your power tubes and your output transformers if it starts leaking DC voltage, because there's a high voltage over here. This is a plate voltage over here. If you follow that line over there, that's high voltage. It's also got the audio superimposed on it, but it's like at, I want to see what it is. It might be at 100 and something volts, right? 200 volts. Let's see that there. I can't see any more voltages on here. This is a bit, very few voltages on here. But there's another filter cap here that's a 350 volt. You can get a clue that this is high voltage because it's coming from the B plus supply. There's obviously a voltage drop over here as well because of that resistor. The current goes there and then it goes through to the plate. So that's at high voltage and you want this at 0 volts. That's why you got that capacitor that's supposed to block the DC voltage. If DC goes through, then this is no longer at 0 volts. Let's say this goes to 4 volts instead of 0 volts. Now your difference between there and there would be 1 volt, and that means a lot of current will flow, a lot of current would flow through. So your bias is thrown out, and that can make this tube run away and pass too much current. And if your fuse doesn't blow, it can overheat your output transformer and actually burn it out. So I check that first. This capacitor here, okay, this one here, is this, it's called a cathode bypass capacitor. And what this does is it acts as a short to ground for high frequencies. Now, what is high frequency? Well, anything above DC is sort of high frequency, right? The minute you get a fluctuating voltage here, or current creating a voltage here, that's because of the audio over there. That gets shorted to ground, so it increases the gain of this stage for the audio frequencies. And depending on what value of capacitor you have there, that will determine what frequencies get amplified as opposed to which frequencies don't. Now, with a 25 microfarad capacitor, you probably have the full audio range. It's probably got a cutoff at about, I don't know, 70 hertz, 80 hertz. So basically your full audio range is going through. If you had a 0.1 microfarad here, that means you'd be amplifying your high frequencies. You'd create like a tube screamer for a guitar amp or something. But in this case, you just want to get the best gain possible for your audio. So that's what I'm going to do next. I'm just going to check this stage, and I want to show you the result of two things. One is I want to show you the result of those capacitors that I removed. This one, that one. That one I won't show you. It's in the bin. It was chucked. Obviously, it was ripped out of the can. But I want to show you the result of this one, and that one, and perhaps that one. Okay, and then I want to test this EL84 in my new DIY tube tester and see what state it's in. We know it's working. We know we've got some really bad distortion. I don't think it's from this tube, but we'll find out. So let me carry on with that. Enough yakking and looking at schematic for now. In this hobby, there are two ways of progressing, of getting better at what you're doing. One of them is just to learn a lot of stuff. Learn. It's something that I never stop doing. The other one is to be lucky. And sometimes one gets lucky. First thing I would do, as I've mentioned, is to check the EL84, the components around it, the connections and everything that attached to it. And there isn't really much. There's a bias resistor, R20, which is a 140 ohm half watt resistor, wire wound. There's that capacitor that does the cathode bypass. There is the grid resistor, R3, which is 1K. And then there is the 1 meg R19, which is the grid leak resistor. Now, look what I found. The first resistor I went to check was this guy over here, which is this is the 140 ohm. It's actually written on the side here. There's also that electrolytic capacitor in parallel with it to ground. That's a ground point over there. Huge lug over there. Okay, so I connected my multimeter to ground, and I wanted to measure this resistor. So the first thing I did is I looked for pin number 3, I think it is. 1, 2, 3. I think that's it. And I was looking for 140 ohms, and I got 16 meg. 16 megs. 10 meg. This is just floating everywhere, but it's anything but 140 ohms. So immediately I know this resistor is open. And I see like a bubble over here. So that could have really been the reason. This thing must have... no, it's actually on both sides. So it's probably a feature of the construction of this particular resistor. But this resistor is open. It's 140 ohms, 5%. So the first thing I'm going to do is replace that. And I'll also replace the cathode bypass capacitor. I'm not sure if that's good or not, but I'll replace that anyway. So that seems to be why we had all that wobbling distortion when we were doing when we were checking the audio. I don't know how this thing sounded at all. I mean, I don't know why that EL84 made any noise at all, because there would be no bias. I suppose there would be a bias for the AC because you got the capacitor in place, and I presume that's still there. I also don't know what this has done to the actual EL84, but we'll check that on the DIY tube tester. So first thing I'm going to do, desolder that there. That's the pin. Remove this resistor, replace it. I'll probably use a 150 because I don't have 140s. I'll use 150 ohm 2 watt, and I'll replace that 25 with a 22 microfarad electrolytic. This is a low voltage because this voltage here would always be about 5-6 volts. This thing I believe is a 12 volt electrolytic, so I'll use a 25-35 volt, no problem. Let me get that done, and we'll see these components out of circuit. All right, that's done. What I did here is I took a 150 ohm resistor. The one they had there was 145%, so that would be 147 at worst case. 150, not a problem. I've seen these resistors really go up in value, and in some of these bias circuits you actually see 170, 180. So again, not critical. What I did do is I took the resistor and the 22 microfarad capacitor, and I've actually piggybacked or paralleled the capacitor onto the resistor first. The reason for that is that the resistor leads are longer and sturdier, because this is a 2-watt resistor after all. And you know, put some heat shrink, and then I just soldered it on. This is the big ground lug that we have in there. So I had removed everything from there, which included the wire from the ground for the speaker. So I took everything out, including that ground for that capacitor over there. That was a 2 microfarad filter cap, a electrolytic. It's the one that we see filtering basically creating a third B+, a lower and more filtered B+, but it's still a high voltage capacitor. And I don't have a 2.2, which is what that would be ideally replaced with, but I put a 10 microfarad. That just gives it more filtering. There is nothing other than filtering happening at that point. So the bigger the capacitor, the better. And obviously in those days, capacitors were expensive, so they made them as small as possible. So that's my capacitor there. Just a note, I do use pigtails like on here. And the reason, well, you can barely see that, but do a little pigtail on the capacitor lead, and I cut the old one there. And the reason for that is these solder tags are very sensitive, and there are other components connected to there. And what I do know is that these resistors, this type of resistor, if you heat the lead too much, they can actually just break off. So I try to avoid too much heat on any resistors that lead to a solder tag. So in that case, I used a pigtail over there, and then over here, I did a proper turnaround after cleaning that solder tag, or solder lug. It's really a piece of the chassis that's sticking out there. Cleaned it out properly and soldered those properly to the chassis. And of course, so that capacitor gets done. And of course, the 4.7 nanofarad is over here. That's coming from the plate of the previous tube. What is that? The ABC80 triode. And I removed that, and again used a pigtail down at the bottom, because it's very difficult to get down to the bottom to desolder from the actual tube socket or tube tag, solder tag properly. There's a resistor on there and another wire. So I cut it and pigtailed it there, and then that comes to here, which then meets that resistor, which is the 1K to the grid of the L84, and the 1 meg to ground. Those measure perfectly well. I mean, this thing is like 1.01 meg, and that's like 995 ohms, just under 1K. So those are perfectly fine. Effectively, what we've done is we've finished the power amplifier section over here. But I want to see what those components are like. Okay, I'm not going to test the audio just yet, because I need to do the preamp section, and then I want to feed the audio into the input socket over here, the DIN part, or the input part of this DIN socket. But in the meantime, I want to check what condition those components were in, including the EL84 tube, because with that resistor blown, could mean anything. The tube could have run away, overheated that resistor, and that's what caused the blowout. It could have been this capacitor that messed up the bias, leaked DC voltage to the grid of that tube, which caused too much current to flow, and then the resistor blew out. We don't know. We'll find out. Let's have a look. Starting with the resistor, the problem there is pretty obvious. It's all over the place. I've got a feeling that that 2.2 is actually probably the shield. Yeah, you see that shield, that coating, is probably what we're reading here, because if I touch the coating, it drops down. So that resistor is open. And that's the one I replaced with the 150 ohm 2-watt resistor. What about the capacitors? We'll start with this 2 microfarad capacitor. This is that filter cap that we were looking at on the supply to the EABC80, and that is reading 2.4 microfarads. Not bad. It's actually not bad at all. What's the ESR like? 3 ohms. It's not really too bad. This capacitor could have stayed in there, but since I'm doing swapping out, Might as well renew it. Let's see the other one. This was the 25 microfarads on the as a cathode bypass. It's probably going to be good as well. Well, forget about that. That's at actually no, don't forget about that. That's 17 microfarads, supposed to be 25, so it's a little bit low. ESR 8 ohms. What happens if I put the frequency at 100 kilohertz, which is what you should measure ESR at? 5.6 ohms. Quite high, quite high. Okay, those are the electrolytics, and this was the coupling cap from the previous audio stage. Get this down to 1 kilohertz, which is what I measure capacitors at. 7.8. It should be, oh God, something wrong here. 7.8 nanofarads. So that's really gone high. Just while we're at it, let's see what the others were measuring. This is the other 4.7 that was on the top across the power transformer. 4.7, it's doubled in value. So again, kaput. And this is the one that was all bubbly. This is in the back, that feedback network. Now this shouldn't be too bad because it doesn't really see much high voltage. So I don't understand why this thing's looking so bad. Come on. This is 150 nanofarads. It's doubled in value. 360. So we had to change it anyway. Now let's have a look at the EL84. So we're testing an EL84. So the first thing I do, unclip this from the back, put in the top one, EL84 on the side here. There we go. Now I'll get the tube. Here we are. Plug that in. First position would be the shorts position for anode or plate and screen grid. 200 milliamps. Hit it. That is not going on. Or is it? Nope. Doesn't seem to have any shorts, but in the meantime, I'll set this up. Remember, this is now just doing the screen short test. Now we're looking at conduction, which is fine. It means the heater's working. Now I'm going to set this to the required Funke settings. By the way, I've put a multi-tone pot on here. That 100K pot arrived, and I tried it to see whether it would heat up too much. Doesn't seem to. But now I can, oh, sorry, that's 200. So that's supposed to be 200. And that's supposed to be 100. That's still got the old pot. I might change this one as well. So 200 and 100. Okay. This is suitably high negative, so I will hit it. Now we'll see what we're supposed to get is with U plate or the plate voltage at 200 volts, the screen grid at 100, we're supposed to get greater than 18 for questionable and 27 milliamps for good at 0 volts. So I'll go down. Well, it is conducting. Bloody hell. Whoa, this thing's conducting a lot. This tube is very good. This tube is very, very good. Now, what about, let's have a look. Set that 200. When it starts drawing a bit too much current, the supply wave is a bit. So let's see, 53.4. 53.4. Let me go to minus 1 volt. 41, so that's 12. And that's our, what are we supposed to get? Our S, 11.3, we're getting 12. So the transconductance is fine. We can actually check the mu at this condition. I don't have to go all the way to the operating conditions, but if I want to check the mu just roughly, actually let's do this at operating conditions. I've got that written on the back of the little thing as well here. So I'll put that suitably high. Operating conditions, let me just put that off there, is 250 volts over here. And this one is the same. So 250 volts, about there. Okay. And it tells us that when we get down to minus 7.3 volts, we should have 48 milliamps. That's the standard operating conditions. So minus 7.3. Bloody hell, this is amazing. This thing is perfect. 48 milliamps, exactly what it's supposed to be. Now if I go to minus 8.3, let me just touch that up there a little bit. I'm having a bit of a problem with those reference diodes. They do fluctuate a little bit. So this thing is actually better than perfect. 7.3, I get 49.6. If I go to 8.3, I get 39.1, so that's 10.6. And the standard operating conditions, they tell us that the S should be 11.3, so we're good, we're at 10.6, is it? That's very close. Now, if I've got it at 8.3, and I've got, let's call that 39 milliamps, okay? Now, if I go to 7.3, again, and I want to get 39 milliamps, I'm at 250 volts there, so I come down till I get 39 milliamps. And here I need to adjust this a little bit as well. It's sort of interactive, and it shouldn't be, but it is. $39 milliamps, there we go, 7.3. Okay, that's good enough. So I've dropped, what is that? On 1 volt drop, I had to drop this from 250 to 230, so that tells me that my mu is 20. And according to their specs, it should be 19.5. So what I have determined is that this tube looks good. Let's see the gas test. Ha ha ha. There we go, there's our problem. This tube is incredibly gassy. Whoa, that is bad. That's really bad. I remember I said I thought that tube was gassy because of that powder. That would have been the case if it was inside. In other words, if that white was inside, it would have meant it was gassy. It's actually, whoa, I forgot this thing is hot. Don't do that. Don't do that. Don't do that. Bloody hell. Okay, live and learn. So that tells us this tube is gassy. A lot. I mean, look, I push the, goes to 100. The whole idea of the gas test, you're putting a resistor, 1 meg resistor in series with the grid current. And a gassy tube conducts grid current, whereas a good tube should conduct very, very little. You should see maybe 1 or 2 milliamps. This thing's shooting up to 100. This tube is gone. What a shame. It was reading perfectly, and yet we do one test and find out that this tube is gone. Well, there's... I was going to say my tube test has just paid for itself. No, it hasn't. It's just cost me a bloody tube. I would have put this into the radio very happily, all satisfied, because the sound would have been good, and sooner or later something would have probably overheated because of the gassy condition here. Okay, so we need to replace the LED4. Well, well, sometimes these things tell you what you don't want to hear. And that's where we are so far. We've got a blown tube. We've got quite a few capacitors replaced. We've got one resistor that was open. And that sort of fits because when you've got something like the cathode resistor blown, it usually tells you something's wrong with the tube. Now we found out what it is. Okay, I'm disappointed. Not in the tube tester. Thank you. Thank you. This tube tester is great. But the fact that I need to put in a different LED4. And just by the way, these tubes are getting expensive. I mean, I used to get these things, I used to get JJs for about 11 euros. And I think they're charging 30 something, 40 something now. Crazy, crazy, crazy. But fortunately, I've got some old ones here, or some new old stock here. And so when it comes to replacing this is not too much of a problem, but in the future it may well be. Well, that's where I'm going to leave it for now. I have finished the power section. Here we are again. We worked on this section over here, and just by the way, we replaced that guy over there. So what I can do is my usual thing. All I'm going to paint is what I have actually checked. That, and then that. I don't know about the rest yet, so I leave it. So over here, what we've done is we've actually checked, well, sticking to the convention, I should do this. Actually, that should be red, because it's been replaced. It's no good, or has to be replaced. So that was found to be faulty. That resistor there as well. So the way I do it is I have checked that resistor, so I put a green line through it. I've checked that capacitor and I put a green line through it. And because I've replaced it, I then put a red line through it. There, and also on the capacitor. So now I know those components were swapped out. What else did I check? Well, I checked this. 1K was perfectly fine. The 1 meg was perfectly fine. Also, I've checked this line here to the point where it actually comes from the plate. That's where it's connected to. So I paint that green. And of course, I replaced this capacitor. That is what I've done so far. Now, where are we? We've got the audio coming from this triode in this EABC80. This EABC80 has got 3 diodes and it's got a triode. Now, the way this works is that 2 of those diodes are used to detect the FM on the ratio detector over here, and the other diode is used to demodulate the AM signal to get the audio from the AM signal from the AM bands. And those audio signals then go off to the selector switch over here, which is really an audio selector switch, okay? And this here, this TA, 1 plus 2 is TB, which is aufnehmen, so take off. And where is it? TA, 1 and 2, 1 and 2. So that's our tape. In other words, if you want to record what's going into the power amplifier, you would take the signal with grounded to signal 1 would go into your tape recorder, okay? If you feed a signal between ground and 3, which is 2 and 3, there we go. So 2 and 3, that's your tape going in, okay? So, all right. And there's also a tape in here, 3 and 2. So you could feed a signal in here, that's your audio in, that's your auxiliary input, okay? And the way these switches work, because with the TA selection, the input selection from here, you actually click two buttons. You have to select 2 buttons. I'll show you that when I get to it. This switching is a little bit complex, but it works. Ultimately, what happens is the audio gets to the top here, the top of the volume pot, and the volume pot takes it off there. It goes to this grid of a triode inside the ABC80, which is grid leak bias. There's a 22 megohm resistor here, which creates a bias because our cathode now is at ground. So you need a negative voltage over there. And there are electrons being shot off here. And because this is such a high resistor, it does create a voltage across it. All right. And then the audio comes out and goes to there. But that I'm going to leave for now because I wanted to have a look at this. And I think that's done. And that, my friends, is where I'm going to leave you today because today I'm 1 year wiser. Well, older anyway. And so my wife is looking at me sideways. The fact that I'm working on a video on my birthday, she thinks it's totally crazy. But, you know, when you enjoy what you're doing, this is what you do for fun. This is where I'm going to leave you now. I hope you've enjoyed that. And if you have, click like, share, subscribe, and all that jazz. And if you want to support the channel directly, please do so on Patreon. Links are in the description below and at the end of the video. Once again, thanks for watching. Bye for now and stay safe.